Okay, we'll get started. I think this thing's on. Okay, so today's day 3, and so what we're going to do is follow on a lot of our discussion yesterday on PIV, okay? Let me first get the laser pointer. There we go. Okay. So what I'm going to do today is not one. This was a lecture I put in after the slides were sent out. So you can actually take notes or sit back and sort of relax and just pay attention. Treat it as a talk like at a conference. This is one where I call it kind of a bonus lecture because it's really kind of new work that's been coming out of my lab. What I've tried to do is when I constructed the course, of course, is to teach it as material, not just, hey, here's what my group does. But this is kind of something we've been working on in response to the potential spatial resolution issue with PIV. And so what I want to do is just spend 1 or 2 slides on other things that are out there, and then spend some time kind of giving you kind of an emerging approach, kind of put in some level of research into the educational material as well. Okay? So again, we've talked about this, I think, pretty much at length, is kind of there's a potential need for higher resolution. And what I'll do this is with kind of 2 approaches. I'll just briefly mention an approach that some of you may be familiar with. It's only applicable for sort of non-reacting fluid mechanics. Maybe it'll work its way into reacting fluids. There's a version called Shake the Box out of DLR. And then a lot of work that we've been doing in something that comes over under the hierarchy of optical flow, and we do a particular optical flow method. And I'll explain this and how these work. Okay, so it should be clear at this point that on the very nature of PIV, it has limited spatial resolution. Now, I want to sit back and say, I do not mean to make a case that PIV is wrong, bad, or anything. In fact, I mean, my lab, we use it extensively. In fact, I mean, it's one of our main research tools. It's very accurate. It's very straightforward to implement. And because of all the impressive work that's been doing by researchers for the past 30 years, we really know how to quantify error sources and things like uncertainty, dynamic range, and all the limitations. So it's an outstanding technique. But again, in the context of very high Reynolds number, very high turbulence levels, there may be a need to have higher resolution. And also at the end, I'm going to show you that there's also certain situations where you can't put in particles. And so some of the method I'll talk about can be applied to non-particle based tracer environments as well as quote-unquote seedless velocimetry techniques. Okay? So let's come back to this synthetic case. Okay, this is DNS. We've calculated in DNS governing equations, so we'll count this in terms of the synthetic world as truth, right? This is the actual vorticity structure, okay? And so, again, let's say we put in synthetic particles and treat this as an experiment. And then, again, I've shown this before. This is the vorticity that looks like if you calculate with, say, a 16 by 16 interrogation box and 50% overlap. And let's say we work even harder. Go to 75% overlap, 16 by 16. This is a fairly aggressive style of processing. Again, this is non-reacting. In reacting flows, this is not always possible. You can even push this down if you want to 12 by 12 and get a little bit better. But those are what would be very, very aggressive style of PIV processing. You can still see the structures are filtered. Okay, they look like a low-pass filter. They represent the general large-scale dynamics, whether you go from here, but a lot of the small-scale information is missing. Okay? So this is well known. This is nothing new. In fact, there's been outstanding research by people where PIV is their absolute their focus. There's been many approaches to circumvent the limited spatial resolution. There's very, very good efforts. Okay? So what I want to talk about is just one in the context of combustion system, and then move on to some other techniques that may be useful. But there, again, I do encourage you to go reading as graduate students, postdocs here. You have the opportunity to, again, fill your head with a lot of the literature, and there's a number of outstanding techniques that use many methods, window deformation, et cetera, to increase the resolution of measurements. Okay, so micro PIV really, it goes as the name states, it's designed to investigate the microscopic scales. So again, if you're only really interested in the small scales, there is a way to get around the spatial resolution. You just make your field of view very small, okay? And so examples of this would be, say, in engines, okay? Boundary layers near surfaces. Let's say you're interested in looking near the crevice of a piston. You're interested in looking at the outer wall, okay? These are measurements where the interesting things, at least in the context of that experiment, may be in the small scale. Now, again, I will come back to this. You are missing out on the large scale. Okay? So again, really what this implies is that you put a type of long-distance microscope and you end up going to, very high magnification, m's greater than 1. Okay? And so what this allows you to do, this is just an example. I'm going to show just a work out of Fulker-Seek's group, and where you achieve small field of view with resolution, with vector resolution on the order of 50 microns. And what you can do is you can look near surfaces and you can see, okay, if I have really good resolution, and I can look at small scale structures, but there's always a penalty with this. The field of view covers about 2.5 millimeters, okay? So you are missing out of, again, it's just a dynamic range issue due to the nature of correlation. You're missing out on the larger scale structures. In some ways, this is, like DNS. If you think about it, DNS has a limited number of grid points that you can apply due to the cost of the computation. They can zoom in and make the grid points as small as they want, right? But you only have a certain number, so your dynamic range is what it is, and therefore the largest scale is limited. Okay? And so, but again, you can get quite successful results. These are measurements, again, as an example, that looked at in engine condition and looked at how the law of the wall worked, and it worked very well near wall, and as you moved away from the wall, it deviated quite substantially for certain cycles. So great information can come from this type of measurement. But again, if you're interested in capturing both small and large scale dynamics, something like micro PIV won't work. Let me just introduce you to a measurement. Many people in reacting flows don't know shake the box. How many of you have heard of shake the box before? Okay, so there are. And so this is something that's becoming more and more common. It's now offered via LaVision in terms of a commercial package. Okay, and let me try to describe it. So it's essentially a densely seeded PTV method. Okay, so particle tracking velocimetry. Okay, so it's purely particle based. There's no correlation. In a nutshell, before I do any more lines on here, really what it is what this says. It's a densely seeded PTV. You track the particles in a very dense way, and dense field in a very unique way. Okay, so it's not your conventional particle tracking velocimetry. One of the things that you ultimately have to do, since you're imagining, if you say, okay, if I'm tracking the particles, that's a Lagrangian description, then I have to translate that to an Eulerian description, okay? And that's where essentially the spatial resolution, some of the limitations comes in. So this was developed by Andreas Schroeder at DLR. Really what happens, it has very stringent time requirements. What you have to do is, this is not done where you have single shot measurements. You have to have time resolved information, okay? And it has very stringent requirements on the temporal resolution. You need to be resolving, ideally, the Kolmogorov time scale. So you're actually monitoring the movement of these particles. So this works very well in non-reacting flows, maybe in liquids or certain things that have slower flows. Again, the idea of translating it to very high-speed flows is unknown. I mean, perhaps this has already been pushed for by Andreas. They're making steps every day that are phenomenal. But ultimately, there are certain inherent limitations that will may be prohibitive for reacting flows. So I won't go over this. This isn't work that we do, but it really uses sort of a predictor-corrector scheme. One of the steps are you have particles at some time t equals 0. You identify particles through a certain algorithm. You predict in the delta t what trajectory Based on, let's say, an underlying guess, you produce a trajectory, so you predict the next position, and then you keep through and refining the new process. You delete ghost particles or fake particles. You find through triangulation. You kind of shake the position. I encourage you to go read these papers or this paper. And what happens is ultimately through an iterative process, you can properly track the particles in time. Okay? Once you can do that, you can get evolution of their movement. Okay? And then through interpolation schemes, you can translate to this kind of Eulerian viewpoint. Okay? This is not really something we're going to talk about. I just wanted, in case no one had heard of this, I wanted to say, hey, go find these papers. It's a very interesting read and very nice technique. What you end up getting by the time you got to understand, since you're following the information of discrete particles, they don't always exist everywhere. So they have to be interpolated to an Eulerian scheme. And so this is sort of what limits the resolution. The resolution turns out to be better than, say, time-resolved tomographic PIV, but it's still limited to hundreds of microns. Okay. Okay, so let's talk about a different topic, optical flow. This will be what the remainder of the lecture is. And so I actually pulled a quote directly from the original Horn and Schunk paper, so that we can kind of get on the same page on what optical flow is. Optical flow is the distribution of apparent velocities of movement of brightness patterns in an image. Okay? Optical flow can arise from relative motion of objects in the viewer. So, in essence, the idea is that if I'm a fixed viewer, and let's imagine I have a square with a dot on it, and then that square and a dot moves to some position. If that was, let's say, a white square with a black dot, I can tell basically the displacement of the square by just tracking the black dot, right? I had marked it some region with a pattern, and I watched its movement, okay? Now, you can say that's a very simple idea, but this is kind of what undermines the idea, is that if I have patterns, if you will, or brightness, a field of at least some level of topology of intensity changes, if I can understand how if I can track that from frame 1 to frame 2, then I can infer the displacement. Okay? Another way of thinking about pattern matching. Okay? This was originally developed for machine vision, solid objects, artificial intelligence. It was not developed for fluid mechanics. This is an example where optical flow tracked the movement of soccer players and then ended up using the NVIDIA graphics processor to try to predict and emulate their movement. From a methodological point of view, let's think about what optical flow really is. It determines the apparent 2D displacement of 3D motion within some time. Okay, so this view right here is a good example. Let's say I'm looking right at this sphere, okay? And let's say I can mark it some way, and this thing's rotating, right? From my point of view, I don't see the three-dimensionality, right? If I'm a sensor, when it's put on my object plane, I basically can see this two-dimensional rotation, okay? So really, the whole idea is, again, we're trying to look at the apparent two-dimensional motion, okay, on a sensor, the image plane, from three-dimensional motion on the object plane. I won't get into this today, but you actually can extend this to three-dimensional optical flow, and that'll be quite important in the future of getting fully tomographic type measurements. But that's beyond what we're talking about today. Okay? So, in order to determine the displacement, again, whether it's solid body or whether we're going to get in fluid mechanics, we need a functional relationship between the 3D motion. Okay, remember, we can have anything actually moving in three-dimensional motion in the image plane, and we need a functional relationship in our image plane. Okay? Now, we may also, setting this up generally, we may also need more information that cannot be recovered using this information, this data term. And I'll go up later what I mean by a data term. Once we develop a model that tells us, or once we have some sort of informational or relationship that tells us what the motion should be, ultimately I'll show you that this is solved via a minimization problem. There can be many local minima. The problem can be convex. So at times, we may need more information to push this in the right direction, okay? And so this is what we're going to refer to as a regularization term. Okay, so let's take a look at this. Let's say we have some image brightness. Right now, still think, before you even think anything about fluids, let's just think about just solid objects that have a pattern on them. That's what I want you to think about. Think that you have a ball with checkers on it, whatever you want. You just have some image that has variations in brightness, if you will, okay? So let's say that at any point x, y in the image plane, there's some intensity x, y, and t, okay? This local brightness, right, if I take out a little small part, belongs to a much larger pattern, right? So if I have an image, if I look in a small part of it, there's some pattern, right? And you have the entire pattern, which is an image. As this image evolves in time, what we're going to assume is that the total image intensity that originally started at t equals 0 remains conserved, okay? It can be distributed. If we think about motion, we can move things along, but we're going to say that the total amount, if I were to integrate and sum that up, I have the same amount of intensity, okay? And therefore, that you get the material derivative, okay? Now, if we apply the chain rule, this can simply be written in this manner, where we have a time rate of change, the partial I, partial x, partial I, partial y, and again, the temporal derivative, okay? So again, this approach was originally applied to the motion of solid objects. And again, this is a very good assumption for the motion of solid objects, right? Now, for you people that have more of a fluids mindset, you'll recognize that this is just an advection equation, okay? Now, this is also referred to in the optical flow literature as the 2D motion constraint equation, okay? So it's just an advection equation. And so here's our local velocity, if you will, or displacement over time, okay? And here's the time rate of change of the intensity, okay? So keeping this equation in mind, if we assume that the velocity is constant between any two pairs, which is exactly what you do in PIV, so there's no additional assumption right there, right? The velocity is constant in between two times, then the equation can be integrated in time with Taylor expansion to obtain something called the displaced frame difference equation. And let's take a look at what this, so we integrated the motion constraint equation. If you go back and read the original Horn and Schunk, they don't do this. They actually retain the partial derivatives. I'm not going to discuss that. But let's think about what this equation says for a moment. Okay, we have an intensity at time t naught, okay, and t equals 0. And then we have an intensity at I1 that occurred sometime later. Okay, so really what this does, this describes how the motion, i.e. the velocity of the field, changes the second image with respect to the first, or equivalently, how I could take and warp the second image back to the first with a coordinate transformation. But again, if I assume that the intensity never changes, all velocity is doing is moving stuff around or warping them. If it's pure advection, it's just moving it in a place, right? And if it's got like turbulence or any type of, it's just swirling around. But you can imagine, I don't know if you've ever done this, but you can actually, with advection diffusion equations, you can go and apply them to any photograph and have them all get swirled up or maybe played around with these things. But imagine you could rewind that. One time step, if I knew the velocity, the actual displacement field, I could rewind in time. And if I can, in that motion, if I rewind it, I get the exact same motion at I equals 0. So that's all we're saying, is that if we assume that the intensity is constant, okay, as if it's conserved, all the displacement, all the velocity is doing is moving our intensity around, okay, such that we could, if we knew the velocity, rewind it back, okay, and that's all that this equation says. So again, this little simple pictorial, it puts in kind of a pure advection type argument, but again, you can see we have x, y, and t. We go forth in t, and all we're saying is that if this was moved here, the image at x, y, and t, the sub-image is the same as it is here. This is in the case of pure kind of advection. But we just have, if we don't know the velocity, we wouldn't know that. Yeah. Okay, so you can imagine to solve this, you really have to set up a minimization problem. We'll talk about this. J here is the penalty function because we have to have a method to minimize this, and we're minimizing it with the solution trying to find V. This is what I call the data term, or again, the data term is actually the DFD equation within the penalty function. Okay, so penalty function can take many forms. If any of you've done minimization problems, you know that you could have a quadratic, which is shown here. Example, you could have other functions like a Lorentzian that are a little softer. And so this just shows you how you proceed within a minimization problem. Okay, so you're trying to find the solution integrated over the entire domain, which here would be an image, right? And we're trying to minimize I0 minus I1. Okay, so just a classic minimization problem. Okay. Now at this point, it's appropriate to know that the problem is ill-posed. Okay, there are more unknowns than knowns. Okay, just for the two-dimensional portion, two-dimensional problem, there's two velocity components, but only one intensity. So I don't have a unique solution. Okay? And then I have other issues with the nature of the minimization problem that can actually give local minima. And so just understand this is kind of the ill-posed problem. And let's think about why this happens. We can kind of say physically, let's assume we have kind of an intensity structure in this direction. Okay? There's usually insufficient local intensity information, if you will, to measure the full velocity vector. You usually have enough to get it normal to the intensity structure, but not tangentially. You can think about this. This is what's referred to the aperture problem. I simplified the aperture problem a bit, but let's think about this. If I have some structure that's aligned just in this direction, okay? And if I just zoom in, I can tell the velocity if it's changing the component that's normal to it, okay? But I can't tell anything along the structure, okay? Really, the reason why this comes about, if you, again, we'll go back, the motion constraint equation, which was the advection equation, basically yields a line in Vx, Vy space. So you can have all these possible solutions upon here, okay? And so what happens, you can find, the take-home message is that you can get the component that's normal to the structure, but finding the one that's along the structure called tangentially, you just don't have enough information, okay? Essentially, it's a gradient issue. And we'll come back to that when I talk about this in the context of scalar imaging. So for right now, keep in mind that this can be a difficult problem to solve mathematically. Okay? Now, the other thing I want to point out is that let's say every bit of information you have, let's say every pixel you have, everything moves randomly. Okay? The probability of recovering velocities are very low. Okay? And this is no different to correlation-based PIV. And let me describe that. Let's go back a little bit into the context of PIV, and you're finding how one pattern moves. Let's imagine that within there, those pixels all moved randomly. Okay? And then at next time they all move randomly, what would your correlation look like? It would be essentially a flat line, right? And so you can't detect what the velocity looks like. Okay? So we always need flows to have some level of what mathematics would call as regular. Okay, we need the signal to be regular, and hence why we have these terms called regularization. But now, if everything if everything moves independently, we won't do well. Okay, and at times, even if we have a well-conditioned process, we still need to provide more information. Okay. No matter what the regularization is, if everything moved independently, I mean every little bit of information, like if you had a completely random field, regularization, minimization problem, it won't work. Okay? But now if we have something that's sort of well-conditioned, solid object motion, if I take and throw this bottle across the room and we track it, the solid object, the flow field around that is actually extremely well behaved. And fluid mechanics, except for things like shock waves, are extremely well behaved. Okay? Groups of fluid parcels move in unison, right? only down anything smaller than the Kolmogorov scale, they all move. You may have fluctuations at small scale, but there's still, think about a vortex, you have many fluid parcels moving together, right? So as long as you have reasonable resolution, you have a flow field that is what we would call well-behaved. Now let me be a little clearer. This regularization imposes a constraint on the velocity field, and the solution depends only on the velocity field. It does not impose any type of constraint on the data term, okay, or the displaced frame difference equation. Okay? So it imposes a constraint only on the velocity solution. Okay? Now let's still think in the context of rigid motion. Let's say we have solid opaque objects. Many neighboring points in space will have very similar velocities, and the image intensity pattern varies in a smooth fashion almost everywhere. Again, think of this concept. I have a checkerboard, right? And I move that checkerboard throughout space. I have all these neighboring points, they have the exact same, no matter what I do to that motion, I can give it chaotic fluid motion, but these groups of sort of pixels, if you will, would all move in a very cohesive fashion, okay? There are very few discontinuities, if any, and so from a mathematical viewpoint, the flow field is regular. Okay? Now, again, we may have to apply a regularization term, and this provides a constraint on the spatial continuity of the field. So really, in the context of minimization problem, the way we want to think about this, minimization problem knows absolutely nothing about the physics. Why would it? Okay? And it's mathematics. It doesn't care about fluid mechanics. Okay? But now if we provide extra information to the velocity field, we may be able to get a solution. Okay? So let's look at the original method from Horn and Schunk. Really, again, solid body rigid motion. One way is to minimize the square of the magnitude of velocity derivatives. This is the most predominant used regularizer. This is called the Horn and Schunk regularization. And you think about for solid motion, this actually makes a lot of sense, right? If I move a solid object through space, that's going to be, again, these kind of groups of, everything is kind of moving in unison if you want to think about it. You're really, what you want to do is avoid in the mathematical solution fluctuations, right? Like local fluctuations, there are none, okay? Think about that concept of a checkerboard moving around, going along, like if you were look along some sort of pattern there aren't derivatives, there aren't fluctuations. There may be large-scale derivatives from the motion, but there are not like pixel-to-pixel derivatives, right? And so what you're trying to do is actually smooth the motion. So now you can set up a different type of minimization problem here where you have, again, this data term that has this displaced frame difference equation here, minimizing the fine V. And then you have this regularization, whatever you pick as your regularization. Okay? And then you have lambda, which is a weighting parameter. And what does that mean? Well, your minimization has two processes here, okay? This right here governs the degree in which the minimization problem is allowed to deviate from the requirements set up by this data term. This ultimately is going to minimize it mathematically in the best way it can, okay? You have to pick your minimization algorithm, but you minimize it the best way you can. You may get a completely unphysical solution, okay? Now, what we're going to do is try to bump this up and make this important. So we're trying to constrain the field by some regularization term. And so we're allowing it to deviate from the mathematical minimization problem, okay? And so we're trying to input some level of physics, although some level of physics aren't very good. This is not very good for fluids, but we'll come back to that, okay? So really what we can see here is that you can see if I'm minimizing the gradients in the flow field, I'm smoothing out everything. So for the Horn and Schunk regularization, as lambda gets large, the flow becomes increasingly smoother, okay? So for rigid motion, this isn't bad. This is, again, back to the Horn and Schunk paper. These were synthetic spheres that were tilted to the viewer, and they're allowed to rotate, okay? And we want to get what the motion is. And so they go through their method. Again, this is 1984. Methods are a little bit different. But this is your exact solution, okay? And this is the estimation. Some parts of the flow field look reasonable. Some parts do not, okay? It's not the point of here to say good, bad, indifferent. It's just you did get an estimation. Some regions of the flow field look good, some it doesn't. But we're actually going to move beyond that and now say, okay, that was the general idea. Let's see if we can adapt this to fluids. So fluids create a much more difficult challenge, but they have been applied. Optical flows probably for 20 years. Until recently, many with the Horn and Shunt approach and modifications, and they've had varying levels of success. And most of the time, they're not very successful. What happens, again, as you can imagine, if we're, again, penalizing the gradients, if you will, this regularization tends to overly smooth the gradients, which, again, is not necessarily good in fluid mechanics where we do have actually flow field gradients, okay? And so what we actually do is the gradients that we want, we underestimate them, okay? All right, so there's many ways to get beyond traditional Horn and Shunt approaches, and the way that we've done it in my group is to do something where we work in the wavelet domain, and again, kind of the technique is a wavelet-based optical flow velocimetry. And so this is kind of where we'll not shift gears, but we'll kind of push forward only with this approach. Now, it's not the intention of this introductory material discussion for me to mathematically describe what a wavelet, go over wavelet analysis, wavelet decomposition, reconstruction. But what I want to do is just mention that the reason why you work in the wavelet domain is it has many advantages, okay? And again, at the break, please feel free if you have questions, you can. Wavelets inherently present a multi-resolution analysis, which actually quite nicely matches the multi-scale nature of turbulence. We can start to address a lot of this ill-posed nature of the problem with wavelets. We can actually close the problem even without regularization, and I'll talk about that just by truncating the wavelets. And again, if the aperture problem exists, it doesn't exist in all flow fields, and I'll describe, again, particles, it's not a problem, is minimized, because what happens when you have a wavelet solution, you can think of kind of a wavelet in some ways, or the solution wavelet is really kind of, a wavelet is kind of like a very high order polynomial, okay? And so each local velocity is informed by velocities at nearby pixels, okay? So we get every local solution gets a lot of information from its neighbors around it. Okay, so the idea here is to not minimize the DFD equation with the velocity field. I'm sorry, the sentence there is a little confusing. So let me just say that the idea is to minimize the DFD with the wavelet transform of the velocity, not the velocity field. So we saw in the way that it's set up, you're minimizing to find velocity. Essentially, you're looking at the solution of the velocity field, but minimize the DFD in trying to find the outcome of the velocity field. We don't do this. We minimize the DFD with the wavelet transform of the velocity field, okay? And so this theta here represents a full set of wavelet coefficients. In case we'll go over what a wavelet is, just very simple, but again, we can characterize any signal, whether it's 1D or 2D, with a full set of wavelet coefficients, and you retain all the information. It's just a different way to decompose the signal. Okay, so let's talk about that. So a wavelet light, if you will, super wavelet transform light, is a wavelet is a mathematical function that takes any given function, again, this would be our velocity field, but we'll call it general F, into different scale components, okay? Really, a wavelet transform is the representative of whatever signal or function F we want to. It's represented through a linear combination of basis functions that are translations and dilations of a fast decaying waveform known as a mother wavelet. So a wavelet is just some function itself, and then we can use this function to act on whatever giving signal field function we want to, okay? Okay, so the way that this works, let's just do a couple equations of math, and then there's a pictorial. I think that's a lot better to look at. If we take a wavelet form of F, the way that you take a wavelet form of any function F at scale J and position N, it's the inner product. It computes the inner product. sorry, a wavelet transform of F computes the set of inner products at scale J and position N, and you get something called detailed coefficients. And bear with me for 1 second until we get sort of the pictorial. What we're really trying to do with a wavelet transform is represent any given signal with as little of information as possible, okay? And so what you have, we're going to get a set of detailed coefficients by taking the inner product of our function with this wavelet atom. And the wavelet atom is just a scaled and translated version of some other function, which is called a mother wavelet. So these concepts called wavelets exist. Okay, we can fit them to our scale and position through scaling and translation. We take the inner product with our signal F, and we generate a whole bunch of detailed coefficients. Okay? Now, this is also, the scaling function is associated with every mother wavelet. It gives us a low-pass representation of the function. And such that each scale J and each position N, we generate a set of approximation coefficients through the inner product of F and phi. Okay. All right. Really, what I don't want you to get too worried about what the wavelet transform is doing, but let's take a look at if we put it all together. Really, what happens is if I take a wavelet transform at some scale J, it produces detailed coefficients, both detailed and approximation coefficients. Okay? And then I can just keep doing this at every scale, okay, until I end up with one coarse approximation and a whole bunch of detailed coefficients at every scale that contain all the information of the signal that when I properly reconstruct everything, I end up back with my original signal. So what I mean here is, let's say there's a discrete signal that's 2 to the F, okay? So let's see, if we have, if we were 12 bits, so if F were 12, we would have 4,096 samples, okay? The finest scale is denoted F, and then we have some predetermined coarse scale, C, okay? So C has to be less than F, okay? So if we start the finest scale, we can take a wavelet transform, we end up with an approximation coefficient, and we end up with detailed coefficients. Now, as we keep working ourselves down the scales, these approximation coefficients keep getting split into coarser and coarser approximations, but we leave the details at each scale, okay? So then the transform at each scale operates on the coarse approximation from the previous scale to produce a new coarse approximation and new detail. So think of it as a tree. At each scale, I produce a whole bunch of detailed coefficients, okay, and one approximation. Then I take that approximation coefficient, I act on it again, and I give that another course, and I generate a whole bunch more detailed coefficients. And I keep working my way down to all the information that is needed to represent the signal is contained here. Every one of these things, I have one coarse approximation and a large number all the way up to DF number of coefficients. So again, I'm left with, in this case, if F were 48,096, I'm left here with, if depending on what C were, I'm left with somewhere approaching that number of coefficients. Now, if I truncate and only use a scale that's not 1, then I have a lot less. But anyway, I have a number, all this information can be used to reconstruct the signal. Okay? So let's look at it from a graphical point of view, okay, in case all that description is completely lost. You have to stare at it for a while. This is my original signal. It's 512 pixels long. Now, once I apply a wavelet transform at one scale, the finest scale, okay, I end up with something that looks a lot like it. This is a low-pass version, okay? But you see it only takes 256 components, okay? I've chopped off half the information. And all that information is now contained here. Those are the detailed coefficients. This is the information that is missing. I need to, quote unquote, add it back onto here to recover the original signal, okay? So this is at every point, remember, a wavelet transform is trying to approximate your actual signal with as little information as possible. And I haven't even shown examples of wavelets, what they look like. It doesn't matter for now. We're just assuming we all take what a wavelet is. We don't want to actually try to do that in a lecture format. But right now, what I'm trying to say is that we can do this. We can get this low-pass filtered version, and we can repeat this over and over again to such that you end up with something that ultimately the original signal in terms of wavelet transport has a single approximation coefficient and all of these detail coefficients. That if I take all this information and invert the transform, I will get back the original signal. So this is all of the information to get back to here, okay? Now, what are we doing for a procedure in terms of velocity? So what are we doing in terms of a fluid velocity flow? Well, we use a multi-scale solution, so we start really coarse and then increase the resolution of scale using the result from a previous scale as the initial guess. And we sort of want to get to the results, but let me try to show some of these steps here in case you have questions. So what we need to choose a predetermined coarse scale and a finest scale, and C and L. Both have to be coarser than the finest scale of the images. So for an example, let's say an image has 2f by 2f pixels. The estimation is 2 times 2 to the L times 2 to the L non-zero coefficients, and L can be as large as f minus 1. So that's the amount of information that the transform contains. We can initialize the wavelet transform. We can actually initialize it with 0, uniform field, whatever we want to. And then we start iterating doing the procedure. Again, a lot of the details are not here. But you would loop through the scales from our coarse scale all the way up to our finest scale. We find the solution to the minimization problem. What is the solution to the minimization problem? The solution is the velocity field that appropriately moves the particle fields at each scale and input at the initial guess at the next finer scale. So when we start at a coarse scale, we have very little information. Let's say we're down at C is equal to or something. We only have 4 coefficients that can even describe this thing. So this thing will look like a very uniform looking blob, but it will solve the minimization problem as best as it can. Then we take and use that as the input on the next scale where we have more information, and we get a more fine resolved answer, and we keep working our way up all the way up until we can actually get something that has pretty decent resolution. Now, as a point of clarification, the wavelet transform is never applied to the particle images. It's only applied to the estimated velocity field that evolves the particle images, because it needs to be applied to a continuous field, okay? So we don't apply it directly to the particle fields. Okay, so enough of like bullet points. So let's see what we can actually do with this so that you can say, okay, well, maybe I want to rewind and go back and pay attention. So once you see sort of the results. Again, let's go back in our test case. So DNS, the reason we like DNS is why we have an answer. We know if something's right or wrong. Real world, we never know if something's right or wrong. Anybody raise your hand, and when you know your answer is right or wrong, you take data? Absolutely not. Don't raise your hand, please don't. You don't know if the answer is right or wrong. So let's go back to DNS and look at the synthetic problem. This is just isotropic DNS, it's 3000, but we have a particle field, so we could treat it. This is one that we've done our example PIV on several times, right? I've already shown you many results, okay? So again, if you're interested, our first paper is an experiment in fluids where we do this, and let's see what type of answer we can get. First of all, I have to say, I've given you very general context of, hey, you need to go regularize this, or you need to have this. There's many different regularization schemes that can be applied. One you can actually do is add no regularization. It's called truncated basis or implicit regularization. Let's set JR equals to 0, but then let's actually truncate our scales. The reason why we can do that is that if we start just setting wavelet coefficients equal to 0 at the finest scale, then our ill-posed problem goes away. We have more information than we need, okay? Because once we get rid of the scales, half the information is actually contained in the finest scales. If you think it's a didactic problem, it goes 2 to the F. And so if we get rid of our finest scales, let's say, for example, we had, again, 2 to the 12th. So we had a 4096 signal. If we chop off the wavelet coefficients at the finest scale, we only have 2048 left coefficients, right? And so that means we only have to deal with half the information. So since we had two unknowns, those would be in the wavelet domain. They would be 2048 times 2048, which is 4096. Our intensity has 4096 pieces of information. It's a closed problem. If that was confusing, just take my word for it that you can actually trunk the wavelet basis off. We don't tend to like to do that. There's other regularization schemes. There's discrete regularization. We can penalize the field globally through the nth derivative. Horn and shunt. first order discrete scheme, okay? But what we can do is this can be applied actually to the wavelet coefficients instead of directly to the velocity, but they're applied globally with no information to the local flow. Our first paper, well, we use third order regularization, okay? There's also something referred to continuous regularization, which is actually performed on the derivatives in the wavelet domain, and these actually allow very complex regularization, and you can compute cross derivatives. Therefore, you can actually consider the actual local flow properties, okay, instead of just applying something globally. This is what we've done in our updated work. Okay? Now, there's other, if you become interested and start looking in the literature, there's others ways to regularize the flow. You can actually just assume something about the flow. You can make your regularization that the flow is divergence-free. And you can always push the solution toward a divergence-free basis, okay? You can say, I know I have Stokes flow. There's other things, Bayesian estimation, stochastic transport models, neural networks, etc. All I'm trying to say is there's many ways to do this, okay? There's not one right answer. Okay, here's our simple problem test case, where this is results we did previously, third order regularization, discrete approximation. There's the answer. One of the things that we did is that you probably already figured out that if this is a weighting parameter, you have to set that somehow. Typically, this is done ad hoc through kind of brute force. But what we did is tried to remove as much of the user from it as possible, and we basically have a kind of semi-automatic method that uses the known properties of turbulent spectra to optimize it. Okay? And so again, you can read about this. I don't want to spend too much time talking about that. But what it does is, the way that you can think about this is if you look, let's see, black curve is lambda is equal to 0. Okay? That's just a case where we have no regularization at all. Okay? And this is the turbulent spectrum. And then what happens is we can see that as lambda is increased, this high frequency energy is actually removed from the flow. And it basically gets a solution that starts to resemble something that has more and more physics. Now, if we remove too much energy from the flow by making this lambda too large, you basically end up with a flow that's over-smoothed as well. So again, you want to find something. So again, the details are in this paper, but we automatically tune our lambda parameter. Okay. So let's look at some profiles, just instantaneous measurements, if you will. We go through all of this. You don't see all the code churns out. It works. We get results out. And here are just velocity profiles. So again, the beauty of DNS is you have truth, right? That's the black curve. At one point, our algorithm was called this. It's changed. So, but let's say this is the optical flow algorithm. That's the red. And then applying PIV correlation is the blue. Well, hopefully, you'll notice is that the red and the black lie really close to each other, okay? And this is kind of what you get for PIV. It's not bad. If the gradients aren't too steep, the spatial resolution is pretty, you get good answers for PIV. Again, not a criticism. We know what we get. But when you have these strong gradients, you get kind of a low-pass filtering. That's what you see here. But we're able to actually track the flow. Again, this can kind of be quantified in terms of an error, which is if we take our estimation of the velocity and the truth, and we take the RMSE, root mean squared error, over the entire image. You can look, this is essentially what correlation gives you. This is another type of optical flow algorithm, and this was our sort of second generation. Okay, we've moved on to third generation, which has dropped this by another 30–40%. So you can see substantial, more than a factor, about a factor, heading toward about a factor of 2 increase in accuracy. Okay, here are error statistics. The red, okay, are correlation. Again, using state-of-the-art LaVision software. These are the PDFs of the error. And you can see much lower error with the optical flow. So just in terms of the velocity, we're getting more accurate measurements. Okay? Now, one of the best ways to look at this is in terms of the vorticity field. Okay? True vorticity, correlation, again, this is at 75% overlap, the really aggressive low-pass filtering, and again, the optical flow methodology. it'll get better. But you can already see here, just stopping here, this is a substantial improvement. We can actually get the small scale structure, okay? There's no interpolation here. This is the result of the methodology. Now, one thing that you will see is that it kind of has this type of checkered pattern on it. And that's one of the things that we worked really hard for a long time to get rid of in terms of the methodology. And I'll come back to that in a second. But for right now, let's look at the fact that we have a much better estimation of the vorticity field. So if you take slices through these, you have the true vorticity in black. You have what's coming through correlation in blue, which is what's expected, a lot of low-pass filtering. And for many of the cases, a very good tracking of the true vorticity, okay, with the optical flow method. Okay? So again, earlier this year, we changed the way that we do not only processing, but everything. We actually developed a new way to do actually wavelet transform, and that's way beyond here, not classical methods. We do it in a different way. We moved to continuous regularization. We use all new physically relevant regularizations. I won't go into those details because they're not published yet. But let's just say, here's our DNS, which is truth. And here's a very challenging, this is the entropy, okay? That's basically omega dot omega. That's, again, very high resolution PIV. Again, we can see the under resolution of the PIV, and we can see what the entropy field looks like. And now you can see our updated processing, okay? We can, very good reproduction of the vorticity field, very good reproduction of the true entropy field, okay? And if we say, was this worth doing? There's our DNS, and there's the previous, and there's the new. And what you can see here is that when you compare the new to the previous, that kind of frequency, the checkerboarding pattern is gone. In fact, we're getting a very close representation of the actual truth. Okay? So we're quite excited about that. Now, test case 3 as we move on. Now let's actually go in the flame. So all this I've shown you is a synthetic, non-reacting case. You're taking a summer school in combustion, and you signed up for the diagnostics part, laser diagnostics. So we have to apply this in reacting flows for you guys to get your money's worth, okay? So there's a highly turbulent premix flame called the Michigan High Pilot Burner, okay? It's piloted very high Reynolds number, okay? 7,900, case A and case 5A, 58,000. This was actually, one thing I should point out is that within our experimental fluids paper, we showed that optical flow is not just a way to process particle data. You actually should do the experiment differently. You use different seeding, you use different delta T's. So I should mention that. This is a case where we took a colleague's actual data that was taken for PIV, which is not optimized for optical flow, but we thought we would just process it and see how we do. Okay? Okay, so we evaluated the methods 3 different ways. The way that they did it. PIV, 16 pixel overlap, interrogation window, 50% overlap. What we call high resolution, this one's really high resolution. It works, it's hard to do PIV down to 12 by 12 pixel correlation, 75% overlap, and then our optical flow velocimetry. Okay, so here's some of the results. They get washed out a bit on this screen, but we have PIV, high-res PIV, and then the optical flow. What you have superimposed on the highly turbulent premix flame are the CH layers. Okay, and you can see, especially if you look on a laptop, you can see this significant increase in kind of resolution going as we go. We actually can get the detailed small structure, and these actually are not noise. I can show you this through vorticity image. I will show you in a minute that they're not just random noise. This is actually small scale fluctuation. Okay? Well, let's see kind of a utility of this. This is a measurement. This is the velocity vector map, and this is the CH layer. Let's say we zoom in just on this bulge. Okay? And let's subsample everything by factor 2. So if we use kind of conventional PIV, even again, like I said, I still think it's 16 by 16, 70% overlap. You end up with these black vectors. Then the high resolution, which is a kind of a 12 by 12 with 75%, you end up with the red vectors. And then if you use the optical flow, because we get a velocity vector per pixel, that's the blue. So the amount of information that's contained in this little bulge is is quite nice. And what this allows us to do is do detailed statistics actually on the CH layer. For PIV, the probability of detecting something that's a pixel wide is very low, okay? And so this allows us to actually look at measurements conditioned on the CH layer. So finally, this is sort of one of our latest results that, again, we're happy with. Again, but we're just trying to show the potential utility of this. Again, this is the vorticity field, say from the high resolution PIV. This is the vorticity field from the optical flow. And if you look at the turbulent spectra and the dissipative spectra, this is about what you can resolve with the PIV. And we get fully resolved with this velocity, all the way down to the smallest Kolmogorov-Lehm scales, all the way up through the inertial range and through the large energy input range as well. Okay? So not only do we have the high resolution to get the smallest scales, like you could potentially get micro PIV, but you can retain all of the largest scales as well. Now, one thing that some of you may be interested in is it's not confined to just particle images. This algorithm can be applied to scalar images as well. Now, if any of you have ever tried to take scalar images and do a correlation to get the velocity, you know that they fail pretty miserably, okay? Sometimes they work, sometimes, but most of the times they fail. Now, the application of scalar images, I will admit, is much more difficult. This is where that kind of the aperture problem comes alive, because in a particle field, you don't really have intensity structure. You have a lot of dots and particles, and so the very small structures are actually very good for an optical flow technique. But if you have a scalar, you may have a long structure, and if you don't have intensity gradients or along the path where you do not have an intensity gradient, it's very difficult to determine what the velocity is due to the aperture problem. So the barber pole illusion demonstrates this. So this here are scalar structures, right? And they're moving upward, right? We know from the barber pole they're really not, because if I put particles on them, now your eye can tell that they're not moving up. These are the exact same simulations, just one with particles. Once we have the discrete nature of particles, even we're the observer, we can tell which way this is actually moving. But if we just look at these scalar structures, they have this apparent vertical motion, okay? This is actually due to the aperture problem. We have an incredibly hard time discerning which way these structures are moving, because we just don't have enough information. Even our computer, our sensor, we don't have enough gradient-based information to determine that. Believe it or not, your brain's doing a slight minimization problem right now. You're trying to figure out which in the way you have stereo vision, you're trying to figure out which way this is moving, okay? And we need a little bit of help. But once we put particles on it, we can say then we do a much better job. So again, scalar imaging is going to have much more difficult time, okay? The algorithm just is going to have a little bit more trouble trying to figure out which way the structure is moving. And you can kind of identify this again. Let's say we have a 3D structure translating in and out of a laser sheet. We have the cylinder, and we get kind of apparent motion. So we don't really know what's happening there, okay? But again, let's try it. We'll go back to the same test case, this 2D DNS. So we have a scalar field. Let's see if we can get some hope from this. Okay, not too bad. I would say here's DNS that's the truth. Here's the U component coming from optical flow. This is based only on the scalar images, not the particle image, okay? And here's the V component. There certainly are differences, and it's not nearly as accurate as applying it to particle images, but it does give you a reasonable representation. The reason why we've worked on this on scalar images is that there are many situations where you cannot add particles to flows, okay? Confined flows, impulse facilities, right? Hypersonic facilities. There are certain things where you just, I was talking to someone, you take, where's my friend from Central Florida? There you go, way up there. You have very high-speed facility. We know we put particles in there. They basically etch your windows, right? There's many facilities. We have certain environments where we can't actually apply PIV. We can't apply even optical flow with particle-based measurements. So for a long time, it's been, hey, can we do these seedless type of velocimetry measurements where we cannot put particles in there, okay? And this is, at least right now, it's taking a step in that direction. What about reacting flows? Test case 2 is still DNS, but it's 3D now. Non-premixed hydrogen-air combust. So here's a DNS in a box. But here we're going to simulate things. We're going to put a laser sheet through the OH field, okay, will generate a synthetic PLIF signal to simulate that if you went and took an OH PLIF measurement, okay? Imagine you take, this is what signal looks like. We'll go over this actually in the next lectures of how you derive that. We integrate it over the laser sheet thickness, and we generate synthetic OH PLIF signals just to simulate like what we do in an experiment, okay? And now we go through and apply everything, and we look at our algorithms. So again, we have truth, and we have our measurements coming from the PLIF. Well, it's not exactly right, and and there are some places where it has some significant error. But one thing I want to point out is that we compare it to something that's essentially a passive scalar in this field, mass fraction, and we get almost an identical result to a passive scalar. So the first thing we can learn from this is that there's not significant reaction that's messing up the measurement. We're getting roughly the same result between an OH PLIF measurement and a passive scalar. Okay, so that's a very good thing. The differences between the truth and our measurement is now not due to chemical reactivity or picking the wrong tracer. It's basically just due to this aperture problem, not being able to determine motion in a correct manner. The minimization regime is heading off in some places in the slightly wrong direction. But let me come back and finish this by saying, if you had a facility where your choice is 0 velocity information or getting something that represents it reasonably well, this is perhaps a good alternative. Okay? And with that, I'll give some concluding thoughts on this. This lecture was meant to be presented more of a talk you would see like at a conference, right? This is more introducing the idea to wavelet-based optical flow velocimetry. I don't need to go over the concluding thoughts, but again, the motivation for developing this approach was based on needing sort of higher resolution measurements. And so far, we've demonstrated on both synthetic and experimental data, and we're seeing some pretty good progress. Okay, anyway, I'll stop for there, and I'll take questions, if you will, on this, and then we'll have a break and get ready for the next lecture. Yes? Well, ultimately what we want is the velocity, so the energy, if you're meaning the energy cascade, well, that's just a statistical quantity. So you would never be able to take something that's a statistic and get any instantaneous realization. Oh, so if you're a quantity, so you could do that, but then what you're doing is, then you would be minimizing of the problem that has a u squared. Right? And so then whatever you got as your result to get back to the velocity, you would have to take the square root, which would introduce error. So it depends. If you wanted turbulent kinetic energy, and that's the only thing you cared about, then yes, it would probably be it could be I'm not going to say it could be, it potentially could be to generate your minimization problem on that direct variable. But my assumption is that then you have access to nothing else. Okay? So you would have to be careful about that. Okay? Good question. Other questions? Okay. Well, we'll take our break. We'll take 15 minutes. We'll start back at 3:20. Or, yeah, we'll take 17 minutes. 3:20 we'll start back. Because the next lecture is some heavy lifting. It's some spectroscopy. So go get your caffeine.